Today we're going to talk about the finding and matching between the two image. Last video you already know about key points, you already know about the descriptors, and right now we have the two image. How we use the descriptor to find the matching pairs between the two image. There are several ways. First, however, to compare the distance between the two descriptors, such as the differences between them are transformed into single numbers, which we use a simple measure of the similarity. So the first method I want to write here is to find the distance between the two descriptors, called the sum of the absolute difference, SAD, right? That's the sum of difference between the descriptor A and descriptor B. Descriptor A is from image 1 and descriptor B from image 2. B. This one we can find by the last video. We know how to find the descriptor, right? That's the matrix, right? So we had to subtract, find the difference between element into each in each the descriptor, and we sum up all the differences together. Okay, and we find the shortened distance. Okay, and then we find the matching pair between the two descriptors. The second one we call the sum of square differences. Okay, right here we don't use square. Right here we use square of differences, and it's similar as SID. Okay, the difference between the individual component of two descriptors vectors are computed, right? The key difference between the SID and SSD is the sum of square differences instead of the absolute differences. And we call right here as the L1 norm and right here L2 norm, right here. And right here we also mentioned about the one method to calculate the distance between the two descriptors is the Hamming. This one is harder to calculate in the horse case. You remember last video I talked about the horse, the binary and horse, right? In the binary descriptor, the result is returned 0 and 1, right? So we cannot apply these methods. We had to use Hamming distance to calculate the differences between the two descriptors. And we use short case. If you learn about digital logic, the short case means if the two elements identical, the results return 0. If the two elements different, it's return 1. For example, 1 plus 1 equals 0, or 0 plus 0 is equal 0, right? And the differences for example, 1 plus 0 or 0 plus 1 equal 1, right? That's the way it happens in case of the binary descriptor. Formula to calculate the differences between the two descriptor right here, and which one is the better? Right here we have the SID and right here we have the SSD. SID, you can see the plus 2, the straight line right here, and you find the distance, the distance between the two key points, right? But if you do the square rules right here, you apply the right triangle. Okay, you can find the short distance. Okay, a square plus b square, okay, equals c square. So this method it's harder to get the better measure, right? The accuracy measure between the two key points from two descriptor, right? And give us the accuracy result, right? That's the reason we applied SSD into finding the matching pair. So right now we already applied the formula to calculate the distance between the two descriptor, right? And they have one method. For example, we have the n key points in the image 1, m key points in another image. So we take every key point in the second image and we calculate distance with the first image. The key points with smaller distance will be considered as pairs, right? This approach we call the brute force matching. So we brute force matching or nearest neighbor matching. And this one they have elaborated into the OpenCV. We just call the matcher brute force matching, and we find the distance between the two key points. And brute force matching work very well for small key points number, but can be computationally expensive as the number of key points increase. So we have another method called the flans. They use the data structure KD3 to search the matching pairs and avoid exhaustive search for the brute force approach. I mean, flan right here will help us to find the matching pair quickly, faster than the brute force matching. We will mention flans and brute force matchers into the C++ code. They are elaborate in the OpenCV with its call function. But right here, I try explain you the theoretical concept about the finding the match. Okay. So both the two methods, brute force matching and flans, they accept a descriptor distance threshold t. They always have a threshold t, which is usually limits the number of the good matching and another the discard match where the respective pairs no correspondences. Okay, a good pair mean the two positive is the good pair matching pair, and four positive right here is mean the mismatch. Okay. And right here, for example, look at this graph. You can see they calculate the SSD, okay, the result of some of the SSD, the differences between the two key points, okay, and we have the two positive, the good match, and four positives, the mismatch right here. And if we choose the T1 right here, we can with the first threshold T1 is set to maximize permissible SSDs between the two features. Okay, in a way that some two positive matches are select right here, and while the four positive matches are most entirely avoided. You see right here you can guess the two positive, but you avoid a lot of the four positive reside. However, most two positive right here, okay, we are discarded, right? We don't select it, right? We miss this positive right here. It's not good, right? So we increase into the T2. So more positive, two positive matches are selected, but the number of the four positive matches also increasing significantly. So we had to choose the good T threshold value to balance the true positive and false positive. So in the real application, so the false positives match cannot be avoided in most cases. So the goal is always to lower their number as much as possible. And right here we apply the one method to find the matching pair between after we already calculate the distance, small distance. We got a short distance between the two key points from two descriptors. So we find the good one, we select matches, right? And the methods right here we apply to find the good matches is the cross check. And how cross checks work? In the first step, we have for each descriptor in the sort image, you find one or more best matches in reference image, and you switch order of the sort and reference image. You repeat finding the matching procedure between the sort image and reference image. I mean, right here you have one from sort image, you have reference image. You use each descriptor in the sort image. You find one or two or three best matches from the reference image, and you switch order. Okay, right now from the reference image is the sort image, and you repeat the matching procedure. Okay, and continue. You select the key points pairs whose descriptors are the best match in both directions. It means you find the matching in both directions when you switch the sort and reference image. So under scotch matching increase in the processing time is obviously right because we squeeze the order of the source. So it's usually to remove significant number of false matches and should thus always be performed when accuracy is preferred over speed. Another efficient way of lower number of probables is to compute the nearest neighbor distance ratio for each key points. So this method for each key points in the source image right here, and the two best matches are located in reference image right here. We have a reference image separate when that's the first image, and we have second image right here. We for each key point in a source image, we have find the two best matches are located in reference image right here, and the ratio between the descriptor distance is computed. We have to find this distance from two descriptor. Okay, we apply the SID, right? And we find distance for first one, the second one, and the threshold is applied to the ratio to short out the ambiguous matches. I mean, first time you have the descriptor from the first image, and after that we have to find in the two best matches second image. You have to find the difference between from first match, and you find the differences from the second matches, and you get the ratio between the distance for the first metric and the second matrix, and after that you have the ratio, right? You use that ratio to show out the weaker one, the best, and you choose the best one. Okay, you choose the softer one. Okay, right here you have two good best matrix right here, but you choose one of them, which one is better. Okay, you have to find the ratio between the two different from matches from the image right here. So you see from the example right here, the image pass with the associated descriptor A is compared to all the batches with the descriptor db1 and db2. And we got the threshold value is about 0.8. It provides good balance between the two positive and four positive. So normally we got the 0.8. In the code, we also use the 0.8 because this value gives us the good balance between the two positive and four positive. Okay, so in this video, we also explain to you the theoretical concept finding matchings, okay, between the two descriptors. That's it. And we apply some of the methods in the OpenCV library called the brute force matching, okay, and flange, and the finding the nearest neighbor, okay, the nearest neighbor distance ratio. That's the we apply the brute force matching, the nearest neighbor matching, okay, flange right here into the code. And you understand why we use that, because we apply to find the short distance between the two descriptors, right? After that, you apply to find the good matching between the two two descriptors, right? We apply select matchings, use the cross check. We cross check means with the source image and source image, and then you find the matching procedure between the key point. Okay, we select the key point from the descriptors who the best matches in both directions. Okay, and that's it. So let's go to the code. We see how we apply finding matchings between two descriptors. Right here, you can also include the image process and image feature right here. The feature to the right here is they give you the library match brute force matching and flange. And right here, you have to create the match descriptor function. This one, they have several arguments right here. The image source, image reference. They have the keep on sort, keep on reference, and descriptor sort, descriptor reference, finding the match type vector right here. And we have right here we have some string right here, because in the main you can select dynamically which method you want, you type the name of each method and show you result, and they compare the time of each method, which one is better, faster, right? And right here we put the cross check right here. It means this boolean variable. If you say true, they apply the cross check for you. If you say false, is do not apply. Um, they do not apply cross check between the source image and reference image, right? And right here you compare if this you select the match right here, brute force matching. Okay, they compare it. It means they compare the select you choose, and right here it's equally. So you choose this one, so you have to apply. And right here, if you say if the descriptor is the binary, you have to apply the Hamming way. It's mean Hamming formula last time you use sort gate, right? But if not the binary, for example, the host, right? Descriptor, you have used the SID to calculate the norm, the distance between the descriptor, right? So right here, and so this method is quite a long time if you use draw check, right, to find the sort distance. But you have another method I mentioned last time is a flan, right? And we convert the source right here into the flows, right? The tiles flow, right? It means from 0 to 1. You convert binary descriptor to floating points due to the the burst in the current OpenCV. Okay, so we had to convert all this one, and after that you apply the descriptor measures. Okay, use the flange matching. After you find the descriptor, you have to perform the matching test. You find the select finding the matches. Okay, you have several ways. I mentioned before. We have find the nearest neighbors. Right here you have the T to compute the time to stop and to find the result, to end the result, how long it takes, and how many matching points matching between the two descriptors. Okay, right here you have to find the match between the descriptor source, descriptor reference, and matches. Right here there is. And continue. If you choose the k nearest neighbor, k right here is equal to, you find the two best matches. So you have to create the k-name matches right here, and you put all the value into the k-name matches. You call this function, and you also pass the descriptor source, descriptor reference, the k-name matches vector, and two right here, the find the two best metrics. Okay, and you can also find the time, how long it takes to find the result, apply the k nearest neighbors. And so we compare to this method too. Right here the nearest neighbor, and right here the k-names, and they show you how long it takes, okay, to use the k and then to find the matching, okay, matching pairs between the two descriptors. And you remember you apply the descriptor ratio, distance ratio, right? And right here we choose value that 0.8, okay, is give to the, and you after you find all the, you apply the k nearest mixture match, you have the vector right here, and you run all the value into the k and a matrix right here. And if the value, if which one is less than the 0.8 right here, you get it. It means it's the best one, is the source stick, the best emission pair, matching pair. Okay, and you push all into the match right here. And after that, just visualize the results. Right here you create the the matching image right here to show how it look like, and just copy clones from the image reference. And right here you use the function draw the image. Right here you can see how each element meanings into the website. I think it's into the open, go to the open CV, you can see that. Right here, you go to the open CV and you can find the go to the find the what is mean for each one. Okay, and into the main, you also read the two image, and you find in the matching pair between the two image. You had some the function read the key points right here, read the descriptor right here, read the key points right here. Where you can change the last the values, the key points right here, maybe the binary or maybe the hash value, and maybe it's something that's large data or small data. They give you different result. You play with them, and right here you can see that we select the type, what the method you choose to see how the result. For example, right here, we try the push measures right here, and we have the data right here. This means the push, right? Push, and we choose the binary, okay, descriptor, binary descriptor, and select the type right here, the nearest neighbor, and we see our results. And you remember, right, this function help you to read um, the file right here. This function you can write outside, and right here you just call this function to the main. Okay, we apply push matching, cross check, we don't choose them. So I'll see the results. So you find the 2000, okay, we find the 2996 matches key points between two descriptors and in about 8.3 second, right? Uh, Between the two images, right? So what happened? We apply the cross check. This value will be lower or higher, and how long it takes. If we apply the cross check, that's only right here. Say true. We apply the calculate distance, LSD, and cross-check both image remain from the source and reference image to switch the order. I think it takes longer than we don't apply cross-check. Right now we apply cross matching and we apply cross-check, and let's see result. Okay, you can only find 1,700. Okay, 705 matching pair, and it takes about 15 seconds to find the matching pair between the two descriptors, right? So we can place with any data to see how the results, okay? So right now we say I apply the flank right here. It's things much faster way, and cross-check right here is 4. Okay, they resume to use this method. They use the KD3 data structure to find in the matching pair. It might be faster. And right here, for example, I choose the k nearest neighbor. Okay. I encourage you to play with the vector type. It's right here, the type vector. You can see that. Increase the play with that in the code. We use the vectors a lot in the code later. We use the flag matching. Okay, with KNN we find Hansel 2008 a average 96 matching pairs between two descriptor in about 1.8 1.9 seconds. It's really fast, right? We also remove the key points about 1737 key points removed. It's not good matching pair, right? So let's play with them. You can change, okay, and we choose the best methods. So this video to show you the meanings of the finding the matching between the two images relies on the descriptor. Okay, see you next video.